Good morning. In the class which we just in which we covered the portion on dust explosion, we looked at the different types of dust. We found that a dust air mixture is explosive. We also found the concentration below which something like a minimum explosive concentration is required to form a dust explosion, but we also found that dust explosions are numerous and there must be methods to control them. In fact, we looked at the sensitivity of the dust mixtures to explosion. We also looked at the consequences of the explosion in terms of its explosion severity, and also defined something like an index of explosibility, IE, and we said is the product of, let us say, ignition sensitivity and the explosion severity. In today's class we take a slightly different topic, namely we look at physical explosions. That means we are looking at explosions being driven by some physical processes such as the flash vaporization. But before getting into this particular topic, maybe I like to spend a couple of minutes on, since we said dust explosions are dangerous and there are numerous instances wherein they occur, the organic, inorganic dust mixtures are a problem. Something which we did not do was how to ensure that such explosions do not occur, or what are the safety features we incorporate to prevent a major catastrophe involving dust explosion. See, immediately we will say, since we talked in terms of a minimum explosive concentration required, the easiest thing is to make sure that the dust should not form this particular explosive concentration. That means the minimum explosive concentration in the particular chute or in the particular hopper or in the particular system by which the dust is being transported, or in the confinement the dust air mixture is such that its concentration is less than the minimum explosive concentration which we determined for the different dust mixtures. Having said that, an ignition source is always required to start an explosion, but to be sort of able to prevent an ignition source from occurring is always difficult. Only thing is that maybe we should take some precautions such that in the particular conveyor in which the dust is being transported, maybe we should properly earth it such that the chances of forming an accidental spark is less. But this is whatever said and done, ignition sources are present, and the safest thing to do is to ensure that a minimum explosive concentration of the dust air mixture is not formed. This is point 1. Supposing we have to handle concentrations which are greater than the minimum explosive concentration, maybe we have to add some inerts, and some of the inerts which have been added are some substances like Fuller's earth, something like mud powder, what is being added, such that you bring down the concentration from the actual value, and when you add it, maybe the concentration of the particular dust reduces below the MEC value. The other alternative is maybe you make a slurry of the dust and handle the slurry instead of handling the dust air mixture, but again you have to remove the liquid and it's somewhat a laborious process. The other type of safeguards which we could have is, maybe instead of having something like, after all the dust mixture forms a flammable gas mixture, and what we could do is we could have something like, say, phosphorus compounds. And what do these phosphorus compounds do? Something we add something like ammonium phosphate, and when some chemical reactions occur, the ammonium phosphate takes in the active radicals and sort of impedes the chemical reaction, and therefore the type of maximum pressure, the type of rate of pressure rise, namely the severity of the pressure rise, could be reduced by adding such substances. This is a way of inhibiting the fire or the chemical reaction. This is in terms of bringing down the minimum explosive concentration. But in spite of all that, one of the safety features which we talked in case of confined explosions, we could also adapt here, such as providing vents, providing maybe the burst diaphragms, and also providing something like explosion doors in the particular appliance which involves the dust. Let's say explosion doors. What it essentially does is, when the rate of pressure rise, if I plot the pressure as a function of time, well, the pressure increases in an explosion to the maximum PM value. The corresponding to the inflection point, I have the value of dP by dt, which is maximum. What this vent or this burst diaphragm does is, if I can appropriately cause it to burst at or cause it to vent out the burned products or unburned products, or the unburned dust and the burned products of dust, well, the pressure falls over here. And in this case, well, I am guarding against the value of PM happens to be the pressure at which the diaphragm gives way or the explosion door opens, or the value of the pressure rise can also be controlled over here. Therefore, provision of this is important, but we must also remember that when you sort of vent out a fire, you must not vent it out or vent out the explosion, you must not vent it out into the neighboring areas in which explosives might be housed. That precaution must be taken. Therefore, we tell that, well, methods of preventing a dust explosion or somewhat taking some precautions are, maybe try to see that the accidental sparks are not there, such that the fire triangle is not complete. You have fuel, you have air, you have the spark over here, or the ignition source is sort of removed, or maybe bring down the minimum explosive concentration by Fuller's earth or otherwise, or using slurry, or else maybe you just ensure that some chemical inhibitors like ammonium phosphate are added, which brings down the rate of the reaction. This is the method of controlling a dust explosion. Having said this, well, it's time to go get into the physical explosions. Let's see what it is about. Let's start with a few examples, because examples are illustrative and we will be able to study the mechanisms using these examples. Therefore, we get started with the very famous example which we talked in terms of natural explosion. And in this explosion, this is the one which happened in Krakatoa. We said it happened around 1883 or so, in which you have the huge volcanic eruption. And what happened is, you have volcano lava being generated. You have, due to tidal wave, lot of water, seawater getting into the volcano. And the volcano is hot, and the mass of the heated substances, lava, is enormous. Something like, you have the thermal mass of this hot substance is large. Into it, a huge quantity of water is getting in, and the water gets locally heated. That means the ambient pressure is 1 atmosphere. The ambient pressure inside the volcano, mind you, it's not choked, it's also 1 atmosphere. You have the local temperature of water exceeding the ambient temperature at which the water boils. Water boils at ambient under 100 degrees centigrade. You have the temperature here which is so hot that this hot value could be around almost, let's say, 1000 degrees centigrade is the temperature of the molten lava, and this molten lava heats water locally to around 1000 degrees centigrade. But you well know the water cannot exist at these high temperatures of, say, 1000 degrees centigrade as a liquid. With the result, this state is sort of a metastable state. That means the water is something like overheated to a very large temperature, let's say temperature overheated to a very large value. And at this temperature, the water sees the ambient pressure, and at ambient pressure, water can exist only up to a temperature of 100 degrees centigrade, and therefore lot of energy gets locked into the water and it just flashes into a vapor. And this flashing of vapor in this particular volcano generated blast waves or shock waves and we said, well, the shock waves were heard up to a distance of 4,500 kilometers away from the volcano. Such is the power of this physical process of flash vaporization. Flash vaporization is because a metastable water is formed. This metastable substance cannot exist as a liquid. It flashes into vapor. The large volume of vapor compared to the volume of water drives or forms a shock wave or a blast wave which is so strong that it travels over a distance of 4,500 kilometers. Well, this is the first example. We also talked of a smaller example. We said Flin Flon in Canada at a place near Ottawa. We said around in the year 2000 or so, now people wanted to go home early. There was a hot furnace, maybe let's say a crucible furnace or a reverberatory furnace. The furnace is still hot. They still want to go home. They take water in a bucket or a pail and pour it into the furnace. And since the thermal mass of the furnace was still very large, and thermal mass is very much larger than the mass of water which is cooling, the water instantaneously attains a higher temperature, much higher temperature than the normal boiling point at the pressure of 1 atmosphere, and it flashes into vapor and it caused an explosion. We also talked in terms of the explosion at Port Hudson. This is the third example. And in this example, we had a pipeline taking liquid propane, transporting liquid propane at high pressure. At high pressure, the propane, the liquid propane is at the ambient temperature. But at 1 atmosphere pressure, the boiling point of propane is something like minus 42.4 degrees centigrade. Therefore, the propane at ambient temperature and at high pressure comes out. It sees the lower pressure of the atmosphere, maybe 1 atmospheric pressure. Propane boiling point is minus 42.4. It can exist as a gas only at this particular temperature, or a liquid below this particular temperature, and it immediately flashes into vapor. When it flashes into vapor, you know what happens? It absorbs the latent heat from the liquid which is coming out, and you sort of formed a fog. We will take this example for analysis a little later, but all what we are saying is, well, we had the case of a volcanic eruption. This is known as hydrovolcanic type of an explosion, or just a volcanic explosion involving water. We talked of water being poured in a furnace which creates an explosion. We talked of some substances which are at a temperature, which are stored at a temperature higher than the normal boiling point corresponding to atmosphere, which can again cause flash vaporization. We want to quantify this. We want to quantify this for the energy release. We want to see the mechanism by which an explosion will take place. And therefore, let's get into some details of how to go about it. Well, the first point we note is, well, we are always thinking in terms of a metastable condition for the liquid. We say, well, the temperature is overheated much above the boiling temperature, and since it is, you have a certain mass of the liquid which is overheated, it also has a specific heat. Well, the energy content of the overheated liquid, that is, it is at this metastable temperature, it cannot exist in equilibrium at this temperature. It can exist at equilibrium only at the boiling temperature. Therefore, it is at this unstable state, and therefore this is the excess temperature. Its specific heat, let's say, is Cp. We are talking of at atmospheric pressure Cp, and you have the mass of the particular liquid which is available. Well, this is the excess energy which is available. And what does the excess energy do? You know, this particular mass, you know, it has a latent heat of vaporization at the atmospheric condition corresponding to HFG, and therefore part of this mass gets evaporated, mv into HFG, and this heat is derived from this excess energy, or rather mv into HFG is equal to the excess energy contained at this unstable condition, and this is waiting to get released, and it gets released by vaporizing part of this particular mass which is in this metastable state, and therefore we have mv, that is mass which gets vaporized, into the latent heat of vaporization is equal to m Cp into T, that is the overheated temperature, that is the unstable temperature which we call as metastable temperature, minus the boiling point temperature, which let us call it as Tb, small b. Therefore, I can now say mV by m, which is the fraction of the liquid which evaporates, is equal to, I can write it as mV by m comes over here, is equal to Cp into T overheated minus the boiling temperature divided by the value of the latent heat over here. Now, when I consider this, well, this fraction has to be less than 1, but in case the explosion is such that the overheated temperature is very much greater, like in the hydrovolcanic eruption, that means you heat it to extremely large temperatures. Well, this particular formula can give a value greater f greater than 1, which is not possible in practice. In that case, what happens is the water, instead of being saturated, that means instead of forming vapor which is saturated, I also have to take into account like f is equal to the value of Cp into T overheated minus the boiling temperature at atmospheric pressure divided by HFG into the degree of superheat. That means I still form vapor, and this vapor has even a higher volume, and therefore the type of pressure wave which is generated is even higher. Well, I think we will have to look at this under what conditions f is equal to 1, f should be less than 1, or f cannot be greater than 1, in which case I have degree of superheat. But let us look at this particular formulation in a slightly expanded form. See, we are thinking in terms of, let us say, the overheated temperature or the metastable temperature T overheated being very much greater than the boiling point temperature. That means what has happened is, initially I have a liquid which is very much higher, that means it is terribly overheated. Well, the boiling temperature of the liquid can only be much smaller than this, therefore it contains excess energy, it is just waiting to release it, and it just flashes into vapor, and the fraction of this mass which flashes into vapor is what I have written over here. But we are talking of these temperature differences being large. We also talk in terms of the specific heat Cp, we also talk in terms of HFG. And whenever we talk of these things, I cannot talk in terms of a larger number. Let us, for the present, let us assume, let's say, that the degree of overheat compared to the boiling point is, let us assume dT is the amount by which the overheated temperature exceeds the boiling temperature, and let it be a small number to begin with. Therefore, the mass, the energy associated when the non-equilibrium temperature compared to the equilibrium boiling point temperature is greater by dt is m into Cp into dt, which is equal to the small value of energy which is over and above the value of the boiling point. That is, this is the excess energy which this substance has, since its temperature is greater than the boiling temperature locally by some particular amount. Mind you, the ambient pressure is still 1 atmosphere. And what does this energy do? It causes some evaporation. Let us say the mass which gets evaporated is dm, and at atmospheric pressure the value of the latent heat, we say is HFG, is the value of latent heat in joules per kilogram, dm mass is in kilograms, and therefore we can write this equation as equal to dE, let us write it over here, dE is equal to m Cp into dt, which is equal to the energy supplied for vaporization, which is equal to dm into HFG over here. Now, if I were to bring the dm divided by m, take m on the right hand side, I get dm over m is equal to, I get Cp into dt divided by the latent heat over here, dt by HFG. Now, in practice we say, well, the overheating is not by a small amount, but I find that the overheating is T overheated, the boiling temperature is Tb, this is sizable, and therefore what is happening is, in the process from the initial mass of the liquid which is available, a mass mv gets evaporated, and therefore the final mass is equal to of the liquid is equal to m minus mv, and therefore if I were to integrate this equation, I get integral of dm divided by m is equal to Cp dt by hfg, as the temperature from the temperature of the overheated value, that is the overheated temperature, to the boiling temperature, that is when it is releasing a particular mass or it is flashing into vapor. And what happens? Initially I have a mass m, and the final mass of the liquid is m minus the one which is evaporated. In other words, mv is the mass which is evaporated and initial mass is m, and the initial mass of the overheated, that is unstable liquid or the metastable liquid corresponding to the temperature TOV corresponds to m, corresponding to boiling temperature when it evaporates, the mass left is this. Therefore, when I integrate out, I get ln m going from m to m minus mv, and on the right hand side I get Cp. No, but you know, Cp is also a function of temperature, and that is the main reason why we are doing this. Therefore, we say in the region between Tb to T overheated, let us presume that the mean value of specific heat Cp is, let us say, is equal to Cp bar, such that I can take it outside, and then, well, this is corresponding to HFG 1 atmosphere pressure. I can say it does not depend on these temperatures, it is a totally different variable, and then I say it increases in temperature from temperature of the overheated value or metastable temperature to Tb of dt over here, which gives me the value of minus, since overheated is higher, I put this with a negative sign over here, is equal to Cp bar into T overheated minus Tb divided by HFG. Therefore, if I were to look at the left hand side, on the left hand side I have ln of m minus mv minus ln m, which I can also write as ln divided by m, because ln m minus mv minus ln m is equal to ln of m minus mv divided by m is equal to, I get the value as equal to minus Cp bar into the value of T metastable temperature minus the boiling temperature divided by HFG. Now, if I simplify this expression, I get 1 minus mass evaporated divided by the mass of the overheated liquid is equal to minus Cp bar into T overheated minus Tb divided by the latent heat of vaporization, or rather this is the fraction I am looking for, the mass which gets evaporated, and this evaporated mass has a very large volume compared to this. We will put some numbers and see. We get the value of F is equal to mv by m is equal to 1 minus, no, mind you, this is again within the ln of 1 minus this, therefore 1 minus e to the power minus Cp average over the temperature into T overheated minus Tb divided by HFG. This is the expression what we get. Therefore, we find, well, if the value of the latent heat is very high, that means this becomes 0, 1 minus 0, that means nothing gets evaporated. If the overheated temperature is very near to the boiling temperature, well, not much evaporation takes place, and therefore, when I talk in terms of flash vaporization taking place, well, the temperature to which the water or any liquid is locally overheated must be very much higher than this, such that I generate lot of vapor, and this vapor is what, since it has a larger volume, it is in the particular confinement, it creates a higher pressure and therefore a blast wave. Well, this is how we estimate the particular fraction F, but let us go back and try to understand the problem a little bit further by looking at maybe the diagram for, let us say, water or some other liquids in the, let us say, in the temperature versus the volume diagram. You know, in thermodynamics we say, well, pure substances can always be talked in terms of two property rule, and therefore we try to find it out, we try to apply it for steam water mixtures, and therefore let's use this diagram. But before using this, we must realize that whenever we are talking of such things flashing into vapor, why does it happen? As a function, when we say when pressure changes, the boiling point changes, and what is this boiling point? It corresponds to the saturation vapor pressure. As pressure increases, the boiling temperature increases, and therefore it is this variation which essentially causes, maybe at some point the pressure is very high, the liquid is at a high pressure, all of a sudden the constraint of this high pressure is removed. Like for instance, there is a leak, it leaks into atmosphere, corresponding to that you have a lower boiling temperature. This is the original value. When I look at this particular pressure, which is the atmospheric pressure, the boiling temperature is higher, but it was originally at this pressure, therefore it still retains the memory of this. The liquid is at this temperature, but now the pressure is low, therefore it feels that this temperature is sort of a metastable value. It just flashes because it has to reach this value, and this is how a flash vaporization takes place. We have to look at it in the TV diagram, but before I do this, since this particular process, namely the dependence on the boiling temperature with respect to the pressure, is what is used to store gases, many of the gases. Let's take one or two examples such that the problem gets a little more focused. Let's say we consider the example what we use in our kitchens normally is the butane gas. It comes by different names. Let's say, well, I store butane gas in a cylinder. In the kitchen, I have a cylinder, I have a pressure regulator over here, I connect the gas over here through a particular cable to a stove, and this stove has different burner heads. I allow some air to get entrained over here, and I supply the fuel air mixture to the particular burner heads over here. I put my vessel here and boil my water or whatever for cooking. Therefore, in this cylinder I have butane, and if I look at butane per se, let me take you through some properties so that we can put the problem a little more clearly. At 1 atmosphere pressure, butane has a boiling temperature. It boils at a temperature of minus 0.5 degrees centigrade. If the pressure is 2 atmospheres, butane boils at a temperature of 10 degrees centigrade. No, I am sorry, this is 1.5 atmospheres. It boils at 10 degrees centigrade. At 2 atmosphere pressure, it boils at a temperature of 21 degrees centigrade. And if it is at 3 atmosphere pressure, well, the butane, liquid butane, boils at a temperature of 32 degrees centigrade. That means below this temperature, if I were to store butane gas, that means if I can increase the pressure to something like 3 atmospheres, I can store it as a liquid, and that is how the gases are stored in small cylinders. That means the butane gas, which we know by name, we call it as Indian gas, we call it as Bharat gas, whatever these gases are there, these are all commercial names, essentially butane with other hydrocarbons. You store it as liquid, like for instance, maybe I store it at 3 atmosphere pressure, at 3 atmosphere pressure, maybe when my ambient temperature is around 30 or 31 degrees centigrade, well, I have butane as a liquid. And this liquid is in equilibrium with the vapor here. The vapor is also at let's say 32 degrees centigrade, it is a liquid, both are at 30 atmospheres. I also have the gas at 32 degrees centigrade. And when I open my regulator, I get the gas coming at the pressure of around 3 atmospheres, which is not a very high pressure, it enters air, mixes and comes. But supposing by chance, normally the rule is you must keep the cylinder vertical. Supposing I were to keep my cylinder horizontally like this, and let's say my cylinder is full and I have the liquid butane over here, again it is at 3 atmosphere pressure. I allow a hose and connect it to my stove over here, and what is going to happen the moment I open the regulator? Well, the liquid gets into my line, and the liquid comes here, it flashes into vapor, because this liquid which is at a temperature 32 degrees centigrade, this is a liquid at 3 atmospheres, And this liquid, when it comes over here, it sees a pressure of 1 atmosphere, maybe much before when it starts entraining the air. It sees a pressure of 1 atmosphere at which it will boil at a temperature of minus 0.5 degrees centigrade. That means, it is the ambient temperature is something like 30 or 35 degrees centigrade. It is going to just boil off because it cannot exist as a liquid at 1 atmosphere pressure when below its boiling point of above its boiling point of 0.5 degrees centigrade. It just flashes into vapor, and I will have all sort of problems over here. In fact, if the cylinder explodes, let us say, if I consider this cylinder by some mechanism, let us say by heating or otherwise, let us say the cylinder explodes, then what is going to happen? I have the butane liquid now at the temperature of 32 degrees centigrade and a pressure of, let us say, 3 atmospheres. And when the cylinder bursts, the gas immediately, or the liquid, is going to see a pressure of 1 atmosphere. And now I have excess energy corresponding to 32 minus 0.5 into this entire mass into the specific heat. I have so much excess energy available because it has to reach the equilibrium value, and this energy is what causes a spurt in the volume and it leads to an explosion. This is a practical case in which explosion or sort of storage of liquid gases which we use in our daily lives could be a cause for problems. Therefore, we have to handle them carefully, and we have to understand this particular aspect of physical explosions which involve the flash vaporization. Let us get back to this particular one wherein we wanted to plot on the TV diagram the plot for water, and if you know for water we can extend it to further other substances. What we say is, well, I want to find out the region in which water exists, the region in which water and steam exist, the region in which steam alone exists as superheated. Therefore, you will recall on the TS diagram we had something like a dome shape, and in this particular dome shape we said, yes, it is in this region in the left side of the dome wherein we have water as a liquid. We had steam over here on the right side of this. This is all steam over here, and in this region we have water and steam. If I consider a line corresponding to, let us say, atmospheric pressure, well, atmospheric pressure, I heat water, I increase in temperature to around 100 degrees centigrade, 1 atmosphere pressure. Then I go horizontally in the water steam line, and this corresponds to the latent heat which we called as HFG over here. And once all the water has become steam, well, any further heating causes the temperature of water to increase. If I talk of slightly higher temperature, let us plot that higher temperature, let us say let us say higher pressure. Well, the temperature is higher, at the boiling temperature is higher. This is water, it goes over here, and I have the constant pressure line. In other words, at this particular pressure, this is the latent heat of water. That is the latent heat for vaporization, that is the heat required to go from water to this. The line over here on the left hand side is the saturated water line, and the line on the right hand side is the saturated vapor line or saturated steam line. They meet at the triple point, and the triple point temperature is typically around, for water it is equal to 374 degrees centigrade, and the critical pressure, that is the pressure corresponding to the particular point, is 221 bar. This is the temperature for water. You have the water line, steam line, you have the two phase wet steam over here, and therefore let us consider one example. Let us consider the example of, let us say, this water being thrown into the furnace, let us say at Flin Flon. And what is happening? Well, I have T and V. You have the water line, you have the steam line over here. Corresponding to this particular critical point over here, the critical point means there is no distinction between vapor and liquid. Both the density of the vapor is as high as the liquid, it cannot be distinguished. Well, corresponding to something like 221 bar and let us say 374, the specific volume of vapor which we are plotting here, temperature versus specific volume of vapor is around 0.00317 meter cube by kilogram. This is the volume. Now, what is happening? We have atmospheric pressure, atmospheric pressure, atmospheric pressure, and now we have, let us say this temperature is 100 degrees centigrade under 1 atmosphere pressure. We have water which is at 35 degrees centigrade over here, and this water is suddenly, let us say you pour it into a very hot substance at let us say a temperature of the order of let us say 350 degrees centigrade. This is 350 degrees centigrade because the critical point temperature we just now saw is equal to 374 degrees centigrade. Therefore, what happens when I pour this water on a plate or plate having a large thermal inertia which is at this temperature, what is it I do? I sort of push the water into this particular state over here, and this is the state at which water is available to me at this hot condition. But the ambient pressure is still 1 atmosphere pressure, and therefore, this is a metastable state, and therefore, the water evaporates and I get steam at this particular dryness fraction. That means I have so much of liquid and so much of vapor, and if I look at the vapor content, well, the difference in the volume of the fluid here and the fluid here is not very small. We will do a problem relating to that, whereas the volume of the vapor corresponding to saturated is very much higher. You have an intense quantity of vapor being generated from this quantity of water, and that is what creates a blast wave. Therefore, if I have to solve this problem, let us put a few numerals down or few symbols down and again calculate the mass of vapor being formed and the energy which gets released. We have delta E, that is the energy which gets released, is equal to, well, I think we have to have the guidelines of this particular figure. We have temperature versus specific volume, meter cube by kg. Let us say temperature is in degrees centigrade over here. We have the initial line for water at 1 atmosphere pressure. This is water line, comes here saturated water, wet steam, and then saturated vapor goes into superheated vapor. This is the stable boiling temperature at 1 atmosphere pressure. This is the 1 atmosphere line. Now, when suddenly water at this temperature is heated to a value of this high temperature over here, that means this is my locally overheated temperature or my unstable temperature, and therefore, it is not able to say this. Therefore, the excess heat which the water contains it can only exist, final state can only be here, whereas it is locally heated to this. Therefore, the condition, if I say this point is A, this point is B over here, delta E corresponding to 1 kilogram is going to be the condition at A, that is the water at state A which is metastable, the state B which is stable, this is the heat content per kilogram, or rather if I have mass which is equal to m, the total energy, that is the excess energy over here compared to this which it wants to get rid of, is equal to m into HA minus HB. If I talk of HA, well, it is a liquid, and liquid we say is HF, and the corresponding state is A minus HF, this is again water fluid at temperature B into something like m, which is equal to the excess content. Now, when this water, when this excess energy, what does it do? It has to overcome, it has to supply this latent heat, because this excess energy goes into vaporizing the water, and therefore, I have a vapor which is formed which corresponds to HFG over here, or rather I say that this energy which is sort of locked into the water at this metastable state vaporizes and forms mv kg of vapor, and I know that the value of the latent heat corresponding to atmospheric pressure is so much, from here to here is this. Therefore, I get this corresponds to the latent heat, and therefore, mv divided by m is equal to HFA minus HFB divided by HFG. This is in terms of the enthalpies. Therefore, I find this is the mass of water, and what is the energy locked in? The energy locked in is this amount, which is also equal to the value of mass of water evaporated into HFG, so much joules. And it is this energy which drives the explosion, or equivalently, we can tell, well, you form vapor which has a very much higher volume compared to the initial volume, which is very much smaller. And since I generate some vapor having large volume, well, I increase the pressure inside my particular appliance, or inside my volcano, or inside my furnace, and I generate a blast wave. And this is the mechanism by which flash vaporization drives an explosion. Let's do this one particular numerical example so that things become more clear. Let's take this example of the Flin-Flon incident. Let us assume that maybe in a particular furnace which is kept at a temperature, the operating temperature of the furnace would have been higher. The furnace has cooled down to 350, but as it takes more and more time to cool as the temperature decreases, what people do is they take some water, they take 50 kg of water, maybe at the ambient temperature. That day the temperature was, let's say, 20 degrees centigrade, and throw it into this particular furnace. And let's also assume that the thermal inertia of this furnace is large, because furnace has a large mass anyway compared to 50 kg of water. And therefore, what happens, this 50 kg of water, immediately when it is exposed to this particular temperature, that is all along, it just touches the metal, it increases the temperature to something like 350 degrees centigrade. And therefore, at 350 degrees centigrade, the ambient pressure is still 1 atmosphere. The furnace is exposed to the ambient, and therefore it is still at 1 atmosphere pressure, wherein the boiling temperature is equal to 100 degrees centigrade. Therefore, what happens is the water just flashes into vapor. I want to calculate the mass of water which evaporates, 0.1, or which flashes into vapor, .1, and second, I also want to calculate the energy release in this particular flash evaporation process. Therefore, we again draw the TV diagram, because it is the simplest thing to do, or we could use the formula what I derived earlier in terms of fraction is equal to 1 minus E, but then we need the value of Cp. We have steam tables, we have tables for all the liquids, we can do this particular problem. Therefore, when I draw this, I again note on the TV diagram, where V is the specific volume, T is the temperature. The ambient line, let us draw the ambient line, ambient pressure line, 1 atmosphere pressure, 1 atmosphere pressure, 1 atmosphere, the temperature here is 100 degrees centigrade over here. And the volume, if I were to make a note of it, at 1 atmosphere pressure, the specific volume, that is Vf, that is V of the water at this particular point, let us use the same terminology, we use A and B, we said, well, this is the point B at which the boiling temperature, which is a stable point, Vf is equal to, we take it as 0.001044 meter cube by kilogram. What happens is the water is at 20 degrees centigrade, somewhere over here. You suddenly throw it at a temperature of 350, you suddenly increase it to this value, even though the pressure is atmosphere, because the body is this, it attains the temperature of the body. This is what the temperature is like. This is at 350. At 350, the specific volume is equal to 0.001 174 meter cube by kilogram. The pressure corresponding to this particular point of 350, if I were to draw the constant pressure line, if I were to draw a line of constant pressure passing through this particular point, the pressure corresponding to this red line is going to be 16.514 atmospheres. Therefore, what is happening is the moment we throw water at 20 degrees centigrade, it reaches this temperature 350. It can be in equilibrium only at this particular pressure, because this temperature, but it sees only the ambient pressure of 1 atmosphere here, and therefore, I find yes, I need to evaluate what is the value of enthalpy over here, what is the value of enthalpy over here. This is the energy locked in for unit mass of substance. Let's put down the, let's get the values from the steam table. I have HF corresponding to point A over here. HFA is equal to, if I look at the steam tables, I will get the value of HFA is equal to 1344 kilojoules per kilogram. If I take the value of HF at B, point B, which is the normal boiling point, normal boiling temperature of the saturated liquid at 1 atmosphere pressure, the value is 419. And the last thing is the latent heat of water, that is the heat required to change the state from B to the evaporation condition over here, that is the saturated vapor. The heat required to go from here to here is something like HFG, latent heat, which is equal to, at 1 atmosphere pressure it is 2258 kilojoules per kilogram. Therefore, if I were to solve this problem, what is it I am looking at? Let us say the original mass of water is 50 kg. The excess heat which it contains at this particular point is equal to HFA minus HFB over here, because this is stable, this is pseudo stable, this is the heat which is contained, and how much of it, part of it evaporates, m dot mv evaporates into steam, and how much is there to be able to evaporate? It needs 2258, or rather the mass of water, mass of vapor formed is equal to 50 into HFA is 1344 minus I have 419 divided by the latent heat, which is 2258, and this comes out to be equal to something like 20.5 kg. Now, what we find is, if I take a look at the volume of vapor here, the volume here corresponds to 1.6729 meter cube by kilogram. That means, you know, the 20.5 kg of steam at this condition is formed. It has a volume which is maybe more than 1000 times this original volume, and therefore, you find that it just generates a high pressure within the furnace, and you have something corresponding to this energy. I have a wave which is being formed, and therefore, this flash vaporization leads to a blast wave which causes an explosion. I should not really be talking in terms of the pressure being formed. All what I say is a large volume of vapor is being formed, which results in an explosion. And this is the phenomenon behind an explosion. And therefore, to sum up, what we have been talking today is, maybe we are telling that a physical process like a sudden vaporization, because we either overheat a given liquid, or it could be any liquid, or else we operate a liquid like we say butane at high pressure, and when we relax the high pressure to atmospheric pressure, or when we overheat the liquid at atmospheric pressure, there is some lot of energy which gets locked in. And how do I calculate this energy in this particular example, which we forgot to do? Well, the energy which is locked in is, well, 20.5 kg of vapor into the latent heat 2258 is the amount of energy which is locked in this, or alternatively I just say 50 into 1344 minus 419, so much kilojoules is the energy which is locked in, and this gives me the value of energy which is locked in, which in turn drives the explosion. Well, this is all about the case of flash vaporization, but flash vaporization has a lot of applications and it leads to different types of explosions involving maybe the cryogenic storage, cryogenic liquid storage. We will talk in terms of some explosions involving cryogenic liquids in the next class, but we will also see whether we will talk in terms of shock waves, and it is quite possible that the vapor also condenses under some critical conditions. We have something like a metastable vapor being formed. It could also drive a blast wave. Therefore, we will talk in terms of cryogenic liquids and vapors, and also we will take a look at explosions involving maybe bursting of spheres, bursting of vessels in the next class, right? Well, thank you.